Good afternoon, everyone. The topic of my presentation today is a problem that comes about in oil and gas wellbores and in geothermal wells. And it is a problem which involves the loading of hollow cylinders simultaneously to tension and collapse. So it's a fairly well understood classical problem, but the solution that I would like to talk about is kind of an expedient solution that is necessary because often we do not have the luxury of performing elaborate computational analyses using finite element tools. So before I talk about the solution, let me explain the problem as briefly as I can. I don't know how familiar you are with the oil and gas environment, but this problem typically arises, like I mentioned, in oil and gas wellbores and in geothermal wells, where you have very high temperatures. So here in the sketch on my, let me see if I can get here in the sketch on the left is a wellbore, and down here is the oil and gas reservoir, which is a porous and permeable rock. And as we all know, this wellbore is going to extract hydrocarbons over a period of time. And when the hydrocarbons are continuously extracted, the in situ pressure, the pore pressure reduces. And because of the weight of the overlying lithological strata, the reservoir begins to compact. And as you all know, there is a impermeable cap rock over the reservoir, which prevents, which is responsible for the storage of the hydrocarbons itself. And as the reservoir compacts, the overburden has to keep up because of displacement compatibility, and this goes into tension. So now if you go in and zoom in on the wellbore tubulars that are present here, so what you have here is the production liner. This is known as the production liner, and here are the perforations which are which connect the wellbore to the pores in the reservoir. And as the reservoir begins to get compressed, the overburden gets goes into tension, and this tensile strain is transferred to the production liner. And this part of the wellbore is in direct hydraulic communication with the reservoir. So over a period of time, the pressure declines. So the pressure here decreases, and the external pressure here remains the same. This is the pressure created by the overburden of the overlying strata, the radial stress created. So therefore, there is a continually increasing collapse load. And like I mentioned, the geomechanical strain gets transferred. So you're pulling the pipe apart in tension and subjecting it to a collapse load. So we have to determine what the structural limit of this casing is, because this production casing is the basic barrier for the hydrocarbons. If there's a failure of this production liner, the hydrocarbons can escape into the environment outside. So this is basically your barrier, and the integrity of this barrier is very important. So that is one situation where we have to understand how to solve this problem. And just before I go to explain the other problem, just to give you an idea of the magnitude of the problem involved, here I have plotted the depletion pressure in the reservoir. This is typically the order of pressures that you see in high temperature, high pressure wells, So you're looking at 10,000 PSI or thereabouts. And for a typical sandstone reservoir, you can see strains of about 12 to anywhere between 3 to 12%, depending on the compressibility of the rock. So where this is the compressive strain, and a part of this compressive strain is transferred entirely across the overburden all the way up to the wellhead. So you see at least a significant fraction of the strain imposed on the tubulars. So with this in mind, let's go to the other situation. And this happens a lot in geothermal and steam injection wells. So typically what happens is, let's take the example of a steam injection well. You have a very viscous fluid in the reservoir, and in order to reduce the viscosity before it gets produced, you pump in superheated steam. So when you pump in superheated steam, you're going to create a high thermal stress in the cemented casing. This casing is cemented, in the open hole. And this generates a high compressive stress. So this creates a load, and the temperatures are high enough that you, even if you assume an elastic plastic pipe in an ideal case, you drive it into compressive yield. And when you take the steam, when you stop pumping steam and the wellbore cools back to the geothermal temperature, the casing unloads and you generate a high level of residual tension. And depending on where you begin to unload the pipe, you can even go into tension yield. So, of course, there are hardening characteristics and so on and so forth. So, suffice it to say that you generate a lot of tension in this casing. And these casings, unlike the previous casings, production casings I showed you a while back, are thin-walled tubulars. The production casings close to the reservoir are thick-walled tubulars. So fundamentally, you have the problem of thick-walled and thin-walled tubulars with various OD to wall thickness ratios subjected to simultaneous tension and collapse. So the problem is, how do we calculate the structural limit? So in order to calculate the structural limit in Wellbores, one of the things we do is we use working stress design. In working stress design, as you all know, we try to stay below the yield strength. So we typically are at about 80% of the working yield stress or the nominal yield stress. So the American Petroleum Institute has a collapse regimen known as the API collapse limit, and it is a very well-established method of calculating collapses. But this method is based on elastic criterion. So it was done in the 1950s and 60s based on a whole lot of tests, and there is a lot of tradition to support the use of this equation for working stress design. But when you use the API collapse limit for the situations that I just described a few minutes back, you simply cannot design the wellbores at all. You cannot, you'll find out that none of the tubulars is strong enough. So we have to go into plasticity considerations. And that is what we have to do. Now, again, this is really not a problem because you can throw this problem at finite element analysis on a finite element program like Abacus or anything and work the problem. But unfortunately, when you have to do a design case and work many iterations and so on and so forth, you need a faster computational tool that makes use of some basic principles that allows you to come up with design criteria. And that is why we decided to solve this problem. So this is a sketch that shows what exactly happens when you subject a pipe to tension and collapse simultaneously. So you have the casing here, a hollow cylinder. There is the ID, and here is the OD. And you've subjected to internal pressure, external pressure, and some kind of an axial load, which I have represented by a strain. The strain can either be transferred because of geomechanical transfer from the formation or because of thermal strains that I just talked about. So when any of these conditions changes, there is a stress change in the cross-section of the tubular. So you can very easily imagine now that as we increase one of these three parameters, the ID of the cylinder reaches yield condition. And as we change one of these three parameters, either the internal pressure or the external pressure or some kind of an axial load, the elastic plastic boundary always starts migrating outward. This is kind of something we all study in our strength of materials courses. And finally, the elastic plastic boundary reaches the OD of the pipe, and we have reached the structural limit. So how do we solve this problem? Once again, a fairly well-known methodology. You have the radial equilibrium equation, and then because we are going into the plasticity regime, we have to go into the plasticity flow rules, the Prandtl-Royce equations with the yield criterion. And here is the hardening. We used isotropic hardening here because usually once you start the plasticity, we don't really unload the pipe. So isotropic hardening is good enough. So with this, it's not very hard to now work these equations out into a finite difference model. And that can be these days Excel and even spreadsheet programs are fairly sophisticated enough that these solutions can be programmed. So here is the stress strain curve of a typical oil and gas casing steel. By the way, I apologize. I've used field units, oil field units, but here are the conversions. So we are talking of about 120 psi, kilo psi. And here is the hardening curve, true plastic strain versus true stress. And the slope of this is what is going to drive the plastic response. So let's take a look at some typical solutions. Here is a casing, about a 7-inch casing with an ID of 2.875 inches. We have subjected it to an external pressure of 16,400 psi and an internal pressure of 5,800 psi. So the radial stress distribution is as it is. So the radial stress distribution does not really change as you change the axial strain. In this simulation, what I have shown is we have subjected it to external and internal pressure and slowly increasing the axial stress. And as we increase the axial stress, you can see that the ID is plasticized here. And as you increase the axial stress, the median surface gets plasticized, and then finally your plasticization is reaching the OD. This is with respect to the hoop stress. And then finally, we look at the triaxial stress, and here is the axial stress, and you will probably see that this is the classic axial stress distribution that you'll see in plasticity textbooks when there is axisymmetric progression of plasticity in a hollow cylinder. So you're reaching the structural limit. So when you put all of this together with hardening, we have to go back to determining the point where the slope of the load versus deflection curve changes sign. So here you have a positive slope, and here the load versus deflection curve has changed sign, which means that you have lost structural strength of the pipe. So with this kind of criterion, we can establish the dependence of the onset of instability on the collapse differential pressure. So here is a set of curves, the same set of curves that I showed you as a function of the differential pressure. So you see you have, as you increase the axial, as you increase the collapse differential pressure, the strain at which your instability sets in decreases, and you can plot this in a pressure tension load path, and this is what we have here: collapse differential pressure on the horizontal axis and the axial strain at which instability sets in as a function of as you reach very high differential pressures. These are the kinds of pressures that we see when at the end of the life of a reservoir, you see you have steep instability setting in. So this is basically like I said, these problems are usually solved by finite element analyses. But like I told you, we needed something a faster turnaround. So this can be easily implemented. These equations can be easily implemented in a Fortran program that can run on a desktop PC. And now that was for the thick-walled cylinders. When you have thin-walled cylinders, what do we do? Thin-walled cylinders, the problem is a little different, because in thin-walled cylinders, there is an initial ovality that comes in because of manufacturing processes. So there is an initial ovality that comes into play, and we have to account for that. And thin-walled cylinder collapse is a fairly well-understood problem in elastic stability. Practically any elasticity book will have solutions for that. So, however, when you apply an axial tension, the problem gets a little difficult. You have to go into some numerical analyses. So here, once again, we go back to some classical methods and apply Rayleigh's criterion for inextensional deformation. So you have a cylinder, and what we are trying to do is we're going to assume that the median surface is inextensional. In other words, what we are saying is that when it is subjected to internal and external pressure, the perimeter of the median surface remains constant. So when you make that assumption, and make the usual assumptions for the first order radial and tangential displacements, you have to introduce a correction. And this correction makes sure that your median surface has a constant perimeter during the deformation. And once you make that adjustment, it becomes a fairly routine calculation, like using the same set of equations and the hardening rules that I showed you a while ago. So here is a two-dimensional grid. I'm going to skip that in the interest of time and show you the final results. So once again, you have a thin-walled cylinder. Here, the D over T of the pipe is of the order of 22. And in the previous examples that I showed you, the D over T was of the order of 11 to 14. So thick-walled cylinders, there is a variation of stress. Here, the variation of hoop stress across the wall thickness is negligible. So here is the major axis hoop strain, the external pressure, which is a proxy for the differential pressure, and the onset of yield and the onset of instability. And we can calculate the collapse criterion. The point I'm trying to make here is if we use the old API or the American Petroleum Institute collapse criterion, you will come up with very low pressures that this casing will be able to sustain, and the design becomes impossible. And you have to go and use some of these advanced notions, plasticity criteria, to work these problems to determine the onset of instability. I think that's all I had to show. And in conclusion, what I was, we have the simultaneous tension and collapse loading occur in well casings in many situations, geothermal wells and wells undergoing severe compaction. And though well design and well integrity calculations require the assessment of structural limits, and there are methods using FEA, we need a faster method. And so what we did was come up with this simpler algorithm that uses fairly well understood classical methods of elasticity and plasticity. And I think that concludes what I had to show in terms of my work. And I can thank you for your attention, and I'll be happy to answer any questions.